Hello friends, welcome to second part of this lecture number 6. In this case we are going to study force exerted by jet on moving curved vane. In the case second we will learn the force exerted by jet on the unsymmetrical curved vane and when it strikes at one tip and leaves from other tip. In last lecture we studied the force exerted by jet on moving curved vane at the center. In this case we have derived the formula for efficiency, and then we have seen the condition for maximum efficiency as u equal to v by 3. Okay, this condition, and from that condition we have also find out maximum efficiency is 8 by 27 in bracket 1 plus cos theta. And let us learn the second case, force exerted by jet on unsymmetrical curved vane which is moving, and this jet striking at one end and leaves from other. Now in this case what we are going to consider, the jet velocity is v1 at inlet and v2 at outlet. Now what are these other terms? The blade velocity is u. At inlet I am considering u1, at outlet I am considering u2. Alpha is nothing but angle made by the jet with respect to x-axis. What is theta? Theta is the angle of blade, whatever the angle of blade. Okay, so inlet blade angle is theta. Similarly, outlet blade angle is phi. Outlet blade angle is phi. So what is beta? Angle made by outlet velocity, exit velocity. Initial velocity of jet is v1, outlet velocity is v2. So what is vw1? Vw1 is the vril velocity, or I can say the velocity which causes the displacement of plate in x direction, that is vw1. Similarly vw2 at outlet. So what is vf1 and vf2 are flow velocities. Now these inlet triangle and outlet triangles are quite important for calculation of force. Let us learn one by one. So this is inlet triangle and outlet triangle. So again I repeat, what are v1 and v2? Inlet and outlet velocities of jet. u1 and u2 peripheral velocity of blade at inlet and outlet. Alpha and beta are the absolute velocity mix with respect to direction of x-axis angle. So angle of absolute velocity of jet with the direction of motion at inlet and outlet. And vr1 and vr2, so these are relative velocity at inlet and outlet. So we know vr1 is nothing but v minus u, and in this case vw1 and vw2 vril velocity at inlet and outlet, flow velocities at inlet and at outlet. Area, again same, cross sectional area of jet is the okay. Learn next thing. So in this case we are assuming that no loss of impact of jet on blade velocity and the fluid friction is 0. In this case we are neglecting that friction from inlet to outlet. Now we can calculate the force exerted by jet in the direction of motion of vane as Fx equal to mass of water striking, that is mass flow rate, in bracket initial velocity minus final velocity. In this case horizontal component of vr1, so horizontal component of vr1, that is effective relative velocity which will push that blade in x direction, is nothing but relative velocity. So what is horizontal component vr1 is nothing but this component, this must be. So how will you get vr1 of horizontal component VR1 into cos of theta, so we will get this side. Similarly, minus horizontal component of VR2 in the direction of motion at outlet, so VR2 in the direction of motion of outlet, we get this position in backward direction as VR2 cos phi. Okay, so I can say mass flow rate is nothing but rho a VR1 or V minus U in bracket VR1 cos of theta. So VR1 cos of theta minus of, this is negative, so minus of minus VR2 cos phi outlet blade angle. So VR1 cos theta minus minus become plus VR2 cos phi. So what we know VR1 cos theta? VR1 cos theta is nothing but C into D, CD, length CD. So what is length CD? Is nothing but total minus this one, we will get CD. So VW1 minus U1. So VW1 minus U1. And what is VR2 cos phi? VR2 cos phi is nothing but this whole length for this triangle. So VR2 cos phi is nothing but U2 plus VW2, U2 plus VW2. Now the final equation becomes rho a VR1 VW1 plus VW2. So U1 and U2 will get cancelled, as we have mentioned that where flow from inlet to outlet, the blade velocity will remain same. So in this case beta is less than 90 degree. So beta is less than 90 degree. So we are getting that rho a VR1 VW1 plus VW2. Now if beta is equal to 90 degree, in that case you will get the next equation as rho a VR1 VW1. Since when we get beta equal to 90 degree, VW2 becomes 0. So this point will shift to this point H. F will shift to H. So VW1 becomes 0 and U2 becomes larger. And in third case, when beta is greater than 90 degree, so this will shift from there. So this angle will be larger. So when beta equal to greater than 90, in that case VW2 will be positive and VR1 cos theta minus VR2 cos theta. So in this case you will get Fx equal to rho a VR1 in bracket VW1 minus VW2. Now work done, as we know, force into displacement. So rho a VR1 VW1 plus or minus VW2 into U. So in this case both cases are considered. It is less than or greater than 90 degree angle. So in few examples they might ask work done per second per unit weight of fluid. So per unit weight of fluid is nothing but mg. So mg is nothing but mass rho a VR1 and g for acceleration due to gravity. So what remains? Density will get cancelled, area. So 1 upon g. So VR1 get cancelled in bracket VW1 plus or minus VW2 into U. Similarly for kinetic energy, half rho a V cube. So efficiency will becomes this rho a VR1 in bracket VW1 plus or minus VW2 into U divided by half rho a V cube. So now in this case again we need to consider that we have assumed vane surface is smooth. So VR1 equal to VR2. If vane surface is different, in that case this will be different and U1 will not be equal to U2. So different conditions of outlet angle made by the absolute jet velocity. So in first case we know this, when beta is less than 90, Fx equal to rho a VR1 VW1 plus VW2. In second case, when beta equal to 90 degree, now it is clear, beta equal to 90 degree, VW2 becomes 0, U2 becomes larger. So in that case equation becomes Fx equal to rho a VR1 VW1. And in third case, when beta is greater than 90 degree, so in this case beta is greater than 90 degree, so VW2 becomes positive as V at outlet is along the direction of jet. So initial velocity minus final velocity. So initial velocity VW1 minus VW2. So these are the real velocity or x direction velocity component which are effective in making the jet in moving along the x-axis. So at the end you are going to learn and explain the impact of jet on moving curved vane when it's symmetrical and unsymmetrical. And in symmetrical we have derived the formula for maximum efficiency and its condition, and in second case the efficiency for unsymmetrical vane and different vane angles and how that vane angle makes the difference in the force exerted by the jet. Thank you.